All right, welcome back. Sound check looks not good, but looks okay. Let me see what device it's okay. So it's my headset. So it's going to be another AI engineering video. In the last video, we started chapter two, and then we got as far as to the architecture section. So the architecture section is going to be a deep dive. I've done a number of deep dives in this channel. Um, this won't be brand new to me. The author does suggest if it gets too technical to skip it, but this is why I like this format of reading out loud in a video rather than just reading myself because it's a clear goal. It's just read every word, put it into uh, my mouth, like actually say the words and move on because otherwise it's if you're just reading it on your own, what do you do? Do you read it 10 times in a row? Do you do an exercise? Like where does it stop, right? And like I think you probably would be pretty tempted to skip it if you were just reading it in your head alone without making like a YouTube video or without uh, having that clear goal of I'm going to take every word on this page and I'm going to read it out loud. That's I feel like that's a good way to kind of set a goal and move on, rather than to skip it as the author recommends in some cases. So, all right, so this is transformer architecture. To understand the transformer, let's look at the problem it was created to solve. The transformer architecture was popularized on the heels of the success of the SEQ to SEQ sequence to sequence architecture. At the time of its introduction in 2014, less than 10 years ago, Seek to Seek provided, and I say Seek because it stands for sequence, provided significant improvement on then challenging tasks, machine translation and summarization. In 2016, Google incorporated Seek to Seek into Google Translate, an update that they claimed to have given them the largest improvements to date for machine translation quality. This generated a lot of interest in Seek to Seek, making it the go-to architecture for tasks involving sequences of text. And yeah, Google Translate has been pretty solid for a long time. They were using the definitive best alternative to something like GPT architecture. At a high level, Seek to Seek contains an encoder that processes inputs and a decoder that generates outputs. Both inputs and outputs are sequences of tokens, hence the name. Seek to Seek uses RNNs, recurrent neural networks, as its encoder and decoder. In its most basic form, the encoder processes the input tokens sequentially, outputting the final hidden state that represents the input. The decoder then generates output tokens sequentially, conditioned on both the final hidden state of the input and the previously generated token. A visualization of the seek-to-seek architecture is shown in the top half of figure 2-4. All right, so this is prior to ChatGPT, the best language-based uh, uh, architecture there was for AI was seek-to-seek. That's what Google Translate used, and we can see that it was RNN based, recurrent neural network based. ChatGPT is GNN, generative neural network, as far as I understand, and it's a transformer. It's GPT rather than seek to seek. So seek to seek, the way it would work is if you're using the phrase "How are you?" question mark. Now you have a uh, final hidden state and interesting. You know what? Let's live in the modern world here and explain this. We'll just go to ChatGPT and say explain this in plain English. Explain this in simple plain English. Let's say that. Explain this in simple, plain English. So we can kind of see as it's thinking there. We see it's quite a bit different. Here you have kind of a sequential, which makes sense because it's sequence to sequence. So yeah, I guess it gives it away in the name because we have a sequence here. How are you? That's a sequence of one word after another, and then there's a hidden state, and then the translation happens to another sequence, which is the translation. Whereas a transformer, which is an attention mechanism, it looks like there's no clear one after another sequence. The how is converted to Como, and then we can see the lines aren't sequential in the same way. So let's see if that. Oh, it looks like it's not ready yet. I don't know what's taking it so long. I'll refresh it. Uh, explain this in plain English. Yeah, it's not even like thinking or anything. Let's try to get ChatGPT version 4 or even 4.0 without the Pro version. Typically is pretty good. So let's get that. Explain this in plain English. Okay, and we could put it up against another. Don't necessarily need the Pro version just for a simple explanation like that. So now we can see that it is thinking, and there we go. It's a lot faster. So imagine you're trying to translate "How are you" into Spanish in seek to seek RNN based sequence to sequence model. First, an encoder reads each word in sequence. How are you? Question mark. It keeps a running summary of all of those words in its hidden state. After reading all the words, the encoder passes just that final hidden state, the blue box in the diagram, to the decoder. The decoder then generates the translation word by word in sequence because it only has one hidden state to work from. It has to rely heavily on the information crammed into that final hidden state to figure out which words in Spanish should come next. Oh, that's interesting. In short, all the meaning from the input sequence is packed into one final hidden state, and that's the main source of information that the decoder uses to provide the translated sentence. Okay, that's interesting. So is that why Google Translate would always have such a short limit of like what you could translate? Like, for example, you couldn't translate a whole book with Google Translate. Oftentimes you couldn't even do more than like a sentence or two. Is it because that hidden state is like really restrictively small? Yeah, so transformer attention based is different. Um, Instead of relying on a single hidden state, it uses attention to look back at all the words in the original sequence each time it generates a new word. When the model produces that, it can focus or attend directly to the relevant parts of the input sequence. Um, okay, so that means that at every step, the transformer can pull the entire context, all the words in the input, instead of relying on a single hidden summary. Okay, so the old version, the RNN based seek to seek architecture has to squeeze all the information about the input sequence into a single bottle, the final hidden state, and then the code from that. The transformer uses a more flexible mechanism, attention, to access any part of the input sequence at any time, which often leads to better translations and easier to train. All right, and that's not necessarily why. Um, yeah. Okay, so that doesn't necessarily mean that you have to give it a short passage, but um, but it will tax the system more the longer it is. So it's not necessarily Yeah, really early RNN translation systems did struggle with long sentences because of having to pack everything into a hidden state. Um, but Google Translate itself likely wasn't limited by that. All right, so moving on. Figure 2-4, seek-to-seek architecture versus transformer architecture. For the transformer architecture, the arrows show the tokens that the decoder attends to when generating each output token. There are two problems with seek-to-seek that Vaswani et al. 2017 address in their research. First, the vanilla seek-to-seek decoder generates output tokens using only the final hidden state of the input. Intuitively, this is like generating answers about a book using the book summary. This limits the quality of the generated outputs. Second, the recurrent neural network encoder and decoder mean that both input processing and output generation are done sequentially, making it slow for long sequences. If an output is 200 tokens long, seek-to-seek has to wait for each input token to finish processing before moving on to the next. The transformer architecture addresses both problems with the attention mechanism. The attention mechanism allows the model to weigh the importance of different input tokens when generating each output token. This is like generating answers by referencing any page in the book. A simplified visualization of the transformer architecture is shown in the bottom half of Figure 2-4. Note, while the attention mechanism is often associated with the transformer model, it was introduced 3 years before the transformer paper. The attention mechanism can also be used with other architectures. Google used the attention mechanism with their seek-to-seek architecture in 2016 for their GNMT, Google Neural Machine Translation Model. However, it wasn't until the Transformer paper showed that the attention mechanism could be used without RNNs that it took off. All right, and I need a quick pause. I'll be right back. All right, I'm back. So the transformer architecture dispenses with recurrent neural networks entirely. With transformers, the input tokens can be processed in parallel, significantly speeding up input processing. While the transformer removes the sequential input bottleneck, transformer-based autoregressive language models still have the sequential output bottleneck. Inference for transformer-based language models therefore consists of two steps. Prefill. The model addresses the input tokens in parallel. This creates the intermediate state necessary to generate the first output token. This intermediate state includes the key and value vectors for all input tokens. Decode. The model generates one output token at a time. As explored in Chapter 9, the parallelizable nature of prefilling and sequential aspect of decoding both motivate many optimization techniques to make language model inference cheaper and faster. Attention mechanism. At the heart of the transformer architecture is the attention mechanism. Understanding this mechanism is necessary to understand how transformer models work. Under the hood, the attention mechanism leverages key value and query vectors. The query vector Q represents the current state of the decoder at each decoding step. Using the same book summary example, this query vector can be thought of as a person looking for information to create a summary. Each key vector K um, represents a previous token. If each previous token is a page in the book, each key vector is like the page number. Note that at a given decoding step, previous tokens include both input tokens and previously generated tokens. Each value vector, V, represents the actual value of a previous token as learned by the model. Each value vector is like the page's content. Okay, so I feel like she's really explaining it well here, but it's just kind of not getting into my brain. Let me read this to myself silently a few times, and because I feel like this is a really good explanation. It's just my mind's not super engaged right now. Okay, so how the attention mechanism works is it leverages three vectors. The first vector is the uh, okay. So the three vectors are the query vector known as vector Q, the key vector known as vector K, and the value vector known as vector V. So we'll probably see that in the screenshot I took earlier. No, no, we don't. But we do see different lines here, line colors. So I would guess that that would perhaps correspond to each of those vectors. Um, so let's see what each of these vectors do. So the query vector represents the current state of the decoder at each decoding step. Um, uh, Okay, so I don't think this shows the vectors. We'll probably get another diagram later that shows the vectors. But the key thing to understand of to understand the attention mechanism is that it leverages three vectors: the query vector, the key vector, and the value vector. And the query vector represents the current state of the decoder at each decoding step. The key vector represents a previous token. And then the value vector represents the actual value of a previous token. Okay, so the query vector is like the summary of a um, okay, so the query vector is kind of odd. Like it can be thought of as the person looking for information to create a summary. So it's not the information of a summary. It's not the summary itself. It's kind of an odd explanation. It can be thought of as the person looking for information. So the query vector can be thought of as a person, which is kind of hard for me to imagine. Okay, the key vector is pretty easy to imagine in this analogy. Um, it's the key vector is like the page number in a book. So uh, okay. And then the value vector um, is like the page's content. So you can easily get the page's content if you know the page number. So I would guess that the attention mechanism works similar than that. It indexes each prior thing it receives so that it can easily go back and pay attention to that content because it has numbers with which it can reference it. The attention mechanism computes how much attention to give an input token by performing a dot product between the query vector and its key vector. A high score means that the model will use more of that page's content, its value vector, when generating the book's summary. A visualization of the attention mechanism is the key value with the key value and query vectors is shown in figure 2-5. In this visualization, the query vector is seeking information from the previous tokens. How are you? Question mark. And then the Spanish question mark that goes at the beginning of sentences to generate the next token. So let's take a look at the dot product. Oh yeah, yeah. Okay, so this is something that should be a little familiar to anyone who went through high school mathematics, but definitely probably not something that's stuck very hard. Well, anyway, I need a break. I'll be back. All right, welcome back. Let's make a bit more progress here. Um, so yeah, this is going to be the visualization that explains the attention mechanism. So attention mechanism visualized from Attention is All You Need, uh, Vaswani et al. 2018. So really bad title for a research paper. It almost sounds makes it sound like human attention is the only thing that you need in this case, and you don't need anything else. But that's very wrong on a number of fronts. I mean, first of all, we're not talking about human attention here. We're talking about a attention mechanism based on computer science principles. And then, of course, it's not all you need. There's more than just the attention mechanism that makes this technology happen. But anyway, so remember we talked about the query, the key, and the value vector. So the query is the one that's a bit unusual. It's like the person trying to make a summary. It's not the summary itself. It's not uh, anything else but the person trying to make the summary. And then the key is like the page number, and then the value is like what's on the page, which you can kind of, I guess that kind of makes sense because the person making the summary, what would they do? Well, the first thing they do need to do is know what to summarize. So how would you tell them that? You can give them the page number of the book, have them read that page, the value, and then give you the summary. So attention mechanism visualized. So here it is. So yeah. So matmul, scale, mask, which is optional, soft mask, and then matmul. I'm not sure what that means. And then attention mechanism in action, computing the next token from the previous tokens. So the previous token, how are you? And then upside down question mark, like in Spanish. Yeah, so I don't understand that. The author would say to skip this if you don't understand it, but huh, yeah. Well, anyway, moving on. So figure 2.5, an example of the attention mechanism in action next to its high-level visualization from the famous Transformer paper Attention is All You Need in 2017. Because the previous token, and actually this paper might be the definitive place you'd want to go to to learn about this. Like it might be less confusing in this paper than it is in that book. And the great thing about this, and probably one of the main reasons why this science is advancing at such a high rate, is the open nature of like every aspect of this. Like Ilya Sutskever went to the Open University uh, in Israel, like, and he went there because he wanted to go to college, like when he was 13. And most universities, you have to be a certain age to go to university. So, or there's restrictions where a lot of times children can't go to university, but but so it's just like it's all out there. Like here's the paper, right? You just click. You gotta, here's how it's even categorized with like a clear number for how to find it, so you don't like find the wrong paper, and then you just access the paper through any of these links here. Like it's not like other science. It's like try that for like any other science. Try that to figure out how to reverse your hair loss, right? Like you're gonna have to pay into some journal, and you'd be lucky to be able to use Sci-Hub. It might not even be in their database, the papers that you need to look at. So Sci-Hub is probably your best option, or you can be a billionaire and pay hundreds of thousands of dollars if not more, like universities do to access lockdown paywalled resources. But not if you're studying AI, which is probably a big reason why it's so it's taking off so much. So yeah, so the book used the exact same graphic here from the paper. Yeah, the book is basically just copying the paper in a lot of ways. Yeah, so I would say if you really want to dive in um, and learn more about this, go to the original source, read the paper. It's probably no more difficult to read than the summary of it in the book. It might be easier to read and understand. Because each previous token has a corresponding key and value vector, the longer the sequence, the more key and value vectors need to be computed and stored. This is one reason why it's so hard to extend context length for transformer models. How to efficiently compute and store key and value vectors comes up again in chapters 8 and 9. Let's look into how the attention function works. Given an input x, the key value and query vectors are computed by applying key value and query matrices to the input. Let WK, WV, and WQ be the key value and query matrices. The key value and query vectors are computed as follows. K equals XW subscript K. V equals X times W subscript V. And Q equals X times W subscript Q. The query key and value matrices have dimensions corresponding to the model's hidden dimension. For example, in Llama 2-7b, the model's hidden dimension is 4096, meaning that each of these matrices has a 4096 times 4096 dimension. Each resulting uh, KVQ vector has a dimension of 4096. And remember, K is key, value, and query. So the attention mechanism is almost always multi-headed. Multi-heads allow the model to attend to different groups of previous tokens simultaneously. With multi-headed attention, the query key and value vectors are split into smaller vectors, each corresponding to an attention head. In the case of Llama 2-7b, because it has 32 attention heads, each k, v, and q vector will be split into 32 vectors of the dimension 128. This is because 496 divided by 32 equals 128. So yeah, so the attention of the query key and value equals the soft max of query times k uh, raised to t. I don't know what the t stands for there. It's not shown what the t stands for. I guess I would assume that it's time, but I don't know if that'd be fair to assume. Um, Especially since I thought we were just talking about. I didn't think we were talking about time. I thought we were talking about matrices. Okay, so not sure what that T stands for. We'll probably see it in the paper, and then that's divided by the square root of D, which I'm not sure what that is, and then all that times V. So the outputs of all attention heads are then concentrated. An output projection matrix is used to apply another transformation to this concatenated output before it's fed to the model's next computation step. The output projection matrix has the same dimension as the model's hidden dimension. Transformer block. Now that we've discussed how attention works, let's see how it's used in a model. A transformer architecture is composed of multiple transformer blocks. The exact content of the block varies between models, but in general, each transformer block contains the attention module and the MLP multi-layer perceptron module. Attention module. Each attention module consists of four weight matrices: query, key, value, and output projection. Um, MLP module. An MLP module consists of linear layers separated by nonlinear activation functions. Each linear layer is a weight matrix that is used for uh, uh, linear transformations, whereas an activation function allows the linear layers to learn nonlinear patterns. A linear layer is also called a feed-forward layer. Common nonlinear functions are ReLU, rectified linear unit, and GeLU, which was used by GPT-2 and GPT-3 respectively. Action functions are very simple. For example, all ReLU does is convert negative values to zero. Mathematically, it's written as ReLU of x equals the max of 0 and x. The number of transformer blocks in a transformer model is often referred to as that model's number of layers. A transformer based language model is also outfitted with a module before and after all the transformer blocks, an embedding module before transformer blocks. Okay, so we'll read about that soon. Right now, I'm kind of letting it get away from me. I didn't understand what the T stood for in this equation, so I want to have a conversation about this equation and kind of understand it a bit more fully. So let's feed in a screenshot to ChatGPT. We can use Pro mode. That's good. All right. Now, hopefully, Pro mode works. It looks like Pro mode is down. Oh no, Pro mode is working now, thankfully. Pro mode just takes forever, so I guess we don't have to use Pro mode, but that'll save some time. But I'd rather get a good answer, so I'm willing to wait if the results are worth the wait. But the results of even just the 4.0 are fine, I think, and then 0.1, I think that's fine as well. So it's yeah, probably not necessary to sit and wait, but I'll do that anyway. So as I'm waiting, I'll continue to make progress here. So an embedding module before the transformer blocks. This module consists of the embedding matrix and the positional embedding matrix, which convert tokens and their positions into embedding vectors, respectively. Naively, the number of position indices determines the model's maximum context length. For example, if a model keeps track of 248 positions, its maximum context length is 248. However, there are techniques that increase a model's context length without increasing the number of position indices. An output layer after the transformer blocks. This module maps the model's output vectors into token probabilities used to sample model outputs, discussed in sampling. This model typically consists of one matrix, which is also called the unembedding layer. Some people referred to the output layer as the model head, as it's the model's last layer before output generation. Figure 2-6 visualizes a transformer model architecture. The size of a transformer model is determined by the dimensions of its building blocks. Some of the key values are the model's dimension determine the sizes of the key, query, value, and output projection matrices in the transformer block, the number of transformer blocks, the dimension of the feed forward layer, the vocabulary size. So we can see that all clearly here. Yeah, so we've got the input and then the output. So and then we've also got a positional EMB, which is C times D model, whatever that means. That's not explained anywhere. Okay, so C is the position indices to track, and D model is the model's hidden size. So the EMB takes the input and the positional EMB. The positional EMB is the position indices to track multiplied by the model's hidden size, and then the EMB itself is the I guess it's the embedding, I would assume. Yeah, because embedding isn't. Oh yeah, embedding. So you've got positional embedding and embedding. So the positional embedding and the input is fed to the embedding. The embedding is the model's vocabulary size multiplied by the model's hidden size. So then it goes into the attention. It goes into a transformer block multiplied by the size by n, and then the attention is um, the model's hidden size multiplied by the model's hidden size. NLP, I don't see where NLP is talked about. It was probably in the reading we just went over. Yeah, MLP module consists of linear layers separated by nonlinear activation functions. So that's what we see there. So FF1 is probably a nonlinear activation function. So it's the model's hidden size multiplied by phi4 dimension, and then FF2 is the phi4 dimension multiplied by the model's size, and then we get the output layer, uh, which some people call the head. Yeah, and then the output. All right, so figure 2-6 was a visualization of the weight composition of a transformer model. All right, and with that, I think I need another break. I don't need to necessarily end. I feel like it would be a good ending point. So I guess I'll consider ending because it might make sense to end. Let me look at the clock. If I'm anywhere near the hour mark, I'll end. Um, Let me pause it and be back. All right, welcome back. So I'm gonna make a bit more progress, but I will need to cut this short pretty quick here. So larger dimension values, and I'll do a sound check just in case. There we go. Result in larger model sizes. Table 2-4 shows these dimension values for different Llama 2 and Llama 3 models. Note that while the increased context length impacts the model's memory footprint, it doesn't impact the model's total number of parameters. So this is table 2-4, the dimension values of different llama models. Okay. All right. So llama 3 dash 405B is very large. Other model architectures. While the transformer model dominates the landscape, it's not the only architecture. Since AlexNet revived the interest in deep learning in 2012, many architectures have gone in and out of fashion. Seek to Seek was the limelight for 4 years, from 2014 to 2018. GANs, generative adversarial networks, captured the collective imagination a bit longer, from 2014 to 2019. Compared to architectures that came before it, the transformer is sticky. It's been around since 2017. How long until something better comes along? Developing a new architecture to outperform transformers isn't easy. The transformer has been heavily optimized since 2017. A new transformer that aims to replace, or sorry, a new architecture that aims to replace the transformer will have to perform at the scale that people care about on the hardware that people care about. However, there's hope. While transformer-based models are dominating, as of this writing, several alternative architectures are gaining traction. Interesting. One popular model is RWKV, an RNN-based model that can be parallelized for training. Due to its recurrent neural network nature, in theory, it doesn't have the same context length limitation that transformer-based models have. However, in practice, having no context length limitation doesn't guarantee good performance with long context. Modeling long sequences remains a core challenge in developing LLMs. An architecture that has shown a lot of promise in long-range memory is SSMs, state space models. Since the architecture's introduction in 2021, multiple techniques have been introduced to make the architecture more efficient, better at long sequence processing, and scalable to larger model sizes. Here are a few of these techniques to illustrate the evolution of a new architecture. S4, introduced in efficiently modeling long sequences with structured state spaces, was developed to make SSMs more efficient. H3, introduced in Hungry Hungry Hippos towards language modeling with state space models, incorporates a mechanism that allows the model to recall early tokens and compare tokens across sequences. This mechanism's purpose is akin to that of the attention mechanism in the transformer architecture, but it is more efficient. Mamba, introduced in Mamba, linear time sequence modeling with selective state spaces. Scales SSMs, which are state space models, I think, um, to 3 billion parameters. On language modeling, Mamba-3B outperforms transformers of the same size and matches transformers twice its length. The authors also show that Mamba's inference computation scales linearly with sequence length compared to quadratic scaling for transformers. Its performance shows improvement on real data up to million length sequences. Jamba, introduced in Jamba, a hybrid transformer Mamba language model, interleaves blocks of transformer and Mamba layers to scale up SSMs even further. The authors released a mixture of experts model with 52 billion total available parameters, 12 billion active parameters, designed to fit in a single 80 gigabyte GPU. Jamba shows strong performance on standard language model benchmarks and long context text evaluations for up to a context length of 256,000 tokens. It has a small memory footprint compared to vanilla transformers. Figure 2-7 visualizes the transformer, um, Mamba, and Jamba blocks. While it's challenging to develop an architecture that outperforms the transformer, given its many limitations, there are a lot of incentives to do so. If another architecture does indeed overtake the transformer, some of the model uh, adaptation techniques discussed in this book might change. However, just as the shift from ML engineering to AI engineering has kept many things unchanged, changing the underlying model architecture won't alter the fundamental approaches. All right, so here we go. Here's a Jamba block. Um, this is
structure A, and then this is structure B. So the Jumbo block has a Mamba layer, Mamba MOE layer, Mamba layer, Mamba MOE layer, Transformer layer, Mamba MOE layer, Mamba layer, Mamba MOE layer. And then there are different types of layers. There's the Transformer layer, Attention MOE layer, Mamba layer, Mamba MOE layer. I guess I won't read the details for that. All right, so figure 2-7 showed a visualization of the Transformer, Mamba, and Jamba layers. The image was adapted from Jamba, a hybrid Transformer Mamba language model. All right, so the next one is a lot of clear text here. It looks like this is a natural stopping point because we're going to be talking about model size here, which is kind of a clean next topic. So with that, that's going to be it for this video. Thanks for watching and stay tuned for the next one where we talk about model size.